Hello, today I'll be discussing my findings with respect to the Physics Lab 1 from Coursera's Introductory Physics Lab 1 course. This week's lab focuses on the constant velocity motion. The main physics idea explored here is the Newton's second law, or equivalently, the momentum principle. The Newton's second law states that the acceleration of an object represented here by A is directly proportional to and in the same direction as the net force acting on the object represented here by F net and inversely proportional to the mass of the object represented here by m. In order to predict the final velocity, we carry out the following algebraic manipulations and we end up with the following equation. And equivalently, the momentum principle can be obtained from Newton's second law by starting from the mathematical expression of the Newton's second law, carrying out the following algebraic manipulations, and voila, you have change in momentum equals to the net force times change in time. Now, for the purpose of this lab, we make an important assumption, assuming that there are no net interactions, which means that F net is equals to 0. And if that is the case, then we have that this expression F net over m times change in time becomes 0, and you have that the final velocity equal to the initial velocity, which means that the velocity is constant. Hence, the final position at any small change in time, delta t, can be predicted by the following equation here. Now, in order to get our experimental data, I actually captured an image. I actually captured a video, and here is my video on Tracker so that I can extract the relevant data. And you see that my origin here is at the center of the ball, and we have that the calibration stick is the diameter of the ball, and I have that the axis of this ball is in such a way that is in the x-axis, is in such a way that the ball moves in the x-axis, and is in such a way that the orientation of this axis, we have that the positive x-axis is to the right and the negative x-axis is to the left. And if I play this, I see that Tracker tracks. And so from here, we therefore need to develop our computational model. In order to develop our computational model, we need some parameters. We need the mass of the soccer ball, which is 0.45 kilograms, the ball's initial position vector, which is minus 0.002, 0.0 meter, and we need to estimate the initial velocity. And we do this by taking the first two position vectors and time from Tracker, and we have that the initial velocity is 0.091, 0.0 meter per second. Now, we then plot this. We then see from Python, we have the Python code over here, and if we run this, we have that the ball moves in the positive x direction as we suspected, and we observe that the plot of the position against time has a positive slope with the slope upwards from left to right. This obviously is what we expected with respect to the orientation we used. Now, plotting the experimental data and the computational results on the Google spreadsheet. Note, the experimental data is represented by blue dots while the model is represented by the red line. We observe that they both have positive slopes. The model agrees with the experimental data to a very high degree of accuracy. However, there is a small deviation at the tail end here, and this is because in our computational model, we assume that the net forces of interaction is equal to 0, when in reality the net force is not actually equal to 0 due to the interaction between the ball and the surface in which it moves and gravity. Now, what if we flip the orientation in such a way that the positive x-axis is to the left and the negative x-axis is to the right? And what happens is that we have a negative slope in contrast to the initial positive slope we obtained when we used our original orientation. Now, and this is what you would expect. Now, what does it mean when we say that our observations can be predicted well by a computational model when we set the net force to be equal to 0? It simply means that the net force on the physical object itself can be assumed or can be estimated to be equal to 0. Now, is it possible to say how many pushes and pulls are added together to give the net force? Well, it is actually possible. Such forces could be frictional force between the ball and the surface, gravity, drag due to air blowing the ball sideways, and so forth. Hence, the force balance will be equal to 0. And that ends my lab report. Thank you.